In this video, we're going to use rational exponents to help us to simplify radical problems. So sometimes it is easier to go from the radical form back to the rational in order to simplify. And I'll show you how to do that in the following examples. So here we have the 8th root of x to the 4th. Now remember, when we do rational exponents, the top number is the regular power and the bottom number is the root. So I can change this back over to rational form. That 4 is going to stay on top, and my denominator is going to be the 8. So remember, the radical piece is always going to be your denominator, whereas the power is going to be, your exponent there is going to be the numerator. Now, 4 over 8 is a fraction that we can simplify, right? We can divide those each by 4 and get x to the 1/2. And then once I've simplified as much as possible, depending on what the problem wants, I can either leave it in the rational form or I can change it back over to the radical, which I'll do here. So this would be a square root of x to the first power, which is just the square root of x. So the 8th root of x to the 4th actually simplifies really nicely to the square root of x. For the next one, I don't have any inside power. So if there's no power there, there is a 1. So this would be 25 to the 1 over 6. Again, the outside here is going to be your denominator. And that inside power there will end up being your numerator. Now, this one's a little tricky. It's not that straightforward, but you may recognize that 25 is actually 5 squared. So I can rewrite this as 5 squared to the 1/6 power. And then using our exponent rules, when we have a double exponent like this, we can multiply those together. So you have 2 times 1 over 6. So that's 2 over 1 times 1 over 6 is 2 over 6, which does simplify to 1/3, right? I can divide these both by 2. So this actually becomes 5 to the 1/3 power. And then if I want to change that back over to radical form, that would be the cube root of 5 to the first power, or just the cube root of 5. So sometimes we have to do a little bit of extra digging in order to simplify further. Here I have the 4th root of both of these. So what that will look like is r to the 2 over 4 and s to the 6 over 4. So they both get that denominator of 4. I am going to simplify, so I can divide these both by 2 here to give me r to the 1/2. And then these can also get divided by 2 to give me s to the 3/2. Now notice they both have a denominator of 2 here, right? So they're both square roots. And there's different ways that you can think of this, but one thing we could do is we could take that 1/2 out and raise it as a larger power. And when I do that, I have an r to the first power and an s to the 3rd power left. Now, this would be a square root. And again, that power of 1 is not going to change anything, just like this power of 1 here doesn't. So you actually end up with the square root of rs to the 3rd power. Again, another way you could have recognized this is right back here, that 2 is going to be a square root in both cases. So we're just combining them back together there under a square root. Okay. Next example here, let's change these to the rational form. So that would be a square root there, right? Again, if there's no power there, there's always a 2. And if there's no power here, there's always a 1. So that's x to the 1/2 times. Again, here, there would be a 1. So x to the 1/4. Now think about your rules here. We do have the same base. So when I'm multiplying with the same base, I can add those exponents. You may want to do that off to the side, 1/2 plus 1/4. I do need common denominators. So I could use 2/4 plus 1/4, and I get 3/4. So this becomes x to the 3/4 instead when I go ahead and add those together. And again, if I want to leave it as a rational exponent, that would be fine. Or I can convert this back over. This would be the fourth root of x to the third power. And again, that third power could go on the outside or on the inside. I'm just going to leave it on the inside. It's a little bit cleaner looking if I can't simplify. All right, let's do a couple more examples here. Next one, again, I'm going to change over. And again, don't forget, there's no numbers here. It's always a square root, and the exponent could always be a 1. This is x to the 1/2, and this is x to the 1/3. Now think about your power rules again, your exponent rules. I have the same base, but I'm dividing. So I'm going to subtract those exponents, right? So x to the 1/2 minus 1/3. Now, again, I would probably recommend doing some of this work off to the side. I do need common denominators here. So the first fraction I can multiply by 3/3, and the second fraction I can multiply by 2/2. So that gives me 3/6 minus 2/6, which is 1/6. So this leaves it as x to the 1/6 power, or the 6th root of x to the first power, which is the 6th root of x. I do want to point out as well, I should just go back up to the top for a second here, is that this problem does say to assume variables are positive numbers. So we don't have to worry about on those even roots of having negatives under the power, or having to use absolute value symbols here. So in case you're worried about negatives under the roots or things like that, because it does say positive values only, we don't have to worry about that for these examples. All right, the last one, we're going to do the same thing. This one's a little trickier, but we're going to start with the same process. So again, here, if I don't have a power for an exponent, it's always a 1. If I don't have anything on my root, it's always a 2. So this becomes 3 to the 1/3 power times 2 to the 1/2 power. Okay, now this one is different. Notice that my bases are not the same here, so it's not going to be a straightforward, oh, just add them together, just subtract the exponents or something like that, like we did in the last two examples. So you may be saying, well, what else could we possibly do? So this is a little bit tricky. Again, you probably wouldn't think of it unless you've seen it before. So I'm still going to actually get common denominators here, but it's going to be for a different reason. So as a little trick, try and get common denominators. So I could use a denominator of 6. So the first one I would multiply by 2/2, and the second one by 3/3. And that would give me 3 to the 2/6 times 2 to the 3/6 power. Now I can't add these together because I don't have the same bases. So I'm doing something a little bit different. And again, this is not something that you would probably think of unless you've seen it before. So what I'm going to do next is I'm actually going to do something similar that I did up here. And I'm going to recognize that they both have the same denominators, which are the same kind of root now. So what I can do is I can sort of factor that 1/6 out from both pieces. And that will leave me with 3 to the square power and 2 to the 3rd power. Now, 3 squared is 9, and 2 cubed is 8. And 9 times 8 is 72. So this becomes 72 to the 1/6 power. And then I could go ahead and convert that over to the 6th root of 72, technically to the first power, but again, we don't really need that. So just the 6th root of 72 here. So again, that one's a little bit trickier because we're so used to having the same kinds of bases. But when we don't, we can still do a little bit more, still use those common denominators, but in a different way. So kind of factoring it back out and then simplifying the inside that's left.